Welcome to iLecture Online, and here's another example of how you figure out the forces acting on a charged particle moving through a magnetic field. And what we want to do here is find the direction and magnitude of that force. So let's read the example. It says we have a particle that has a charge of 4 microcoulombs. It's moving with a velocity of 200 meters per second in the x direction and 600 meters per second in the y direction. And it's moving through a magnetic field where the magnetic field strength is 5 teslas in the x direction and 8 teslas in the z direction. Now that is a pretty strong magnetic field. Typically, you don't encounter magnetic fields like that of that strength unless you go in a magnetic imager in a hospital probably. But anyway, that's really besides the point. Let's see what we need to do here. What is the magnitude and direction of the magnetic field? Oh, that's not what I want to ask. I want to ask, what is the magnitude and direction of the force acting on the charged particle moving through the field. All right, that's what we're trying to find. Okay, now trying to draw a picture of that, since it's a three-dimensional picture, may be a little bit difficult, but let me show you how to do it like this, and you probably don't need a picture for that. You can say that the force is equal to Q times V cross B. So what we need to do here is find the cross product of the V vector, the velocity vector, and the magnetic vector, the magnetic field vector. So this is equal to the magnitude of the charge times, and V cross B can be represented by the matrix I, J, and K. That would be V in the x direction, V in the y direction, V in the z direction, and B in the x direction, B in the y direction, and B in the z direction. So we're simply going to do a vector product here. All right, that is equal to the charge times, so we still have the I, J, and K unit vectors. So now let's plug in the values for V in the x direction, the y direction, the z direction. X direction is 200 meters per second, so we write 200. We'll leave out the units to keep it a little cleaner. The y direction is 600, and the z direction is 0 meters per second. And then for the magnetic field strength, we have 5 teslas in the x direction, so we write 5, 0 teslas in the y direction, and 8 teslas in the z direction. So now we're ready to go ahead and solve the problem, solve this matrix. So this is equal to the charge Q times. We'll open up the brackets. Now what goes in the brackets is what's inside the matrix here. We take the unit vector I and multiply that times the product of these two. So when you put the I there, you hide that column, you hide that row, and then you have these 4 elements left. And so now you're going to multiply the I unit vector times the product of these two minus the product of those two. So it would be 600 times 8 minus 0 times 0. So again, it's this unit vector times the product of those two minus the product of those two. All right, now you go minus J. So you alternate signs. So you go plus I minus J plus K and so forth. So now if you hide the row that J is in and the column that J is in, you're left with these 4 numbers right there, those 4 elements. And so now it's minus J times the product of those two minus the product of those two. So it would be 200 times 8 minus 5 times 0. And finally, it's plus K times, and again, you hide the row that K is in, you hide the column that K is in, and now you do a product between those two minus the product of those two. So it would be 200 times 0 minus 600 times 5. Okay, and then of course you multiply that times the charge. Now we're ready to simplify that. The charge was 4 microcoulombs, so it's 4 times 10 to the minus 6 coulombs, multiplied times I, which would be, and of course remember, we're going to be multiplying velocity times the magnetic field. So the units for what's inside the brackets would be meters per second times teslas. So we have 600 times 8 minus 0, which is 4,800. In the x direction, here we have 1,600 in the j direction, but it's minus j, so it's minus 1,600 in the j direction, or the y direction. And here this is 0, that is minus 3,000, so minus 3,000 in the z direction. Okay, so we close the brackets. The units are going to be, since it's velocity times magnetic field, it's going to be meters per second times Teslas. And here, for good measure, we're going to write meters per second times Teslas. And of course, Q has the units of Coulomb. All right, now we should multiply this times each one of those. And for that, we're going to need a calculator. Here's my calculator, hiding in plain sight. So we have 480 times 4 exponent 6 minus equals, and that is 0.192. Is that true? 0 times 10 to the minus, oh, it's 1.92. So this is equal to 1.92 times 10 to the minus 3. The units, of course, for force is going to be newtons times the I direction. Multiply 1600 times 4. 1600 times 4 e to the 6 minus equals, so we have 6.4. It's going to be a minus 6.4 times 10 to the minus 3 in the y direction. And then we have 3000 times 4 e to the 6 minus equals, and that would be a minus, how about 12.0 times 10 to the minus 3 in the z direction times k, and that will be the magnitude and the direction of the force in ijk components. All right, now what if we want to find the actual total magnitude of that force? So we have it in terms of the x direction, the y direction, the z direction. Let's say you just simply want to find the magnitude, F. So the magnitude F can now be found by saying it's the square root of the individual components squared, added together, and I'm taking the square root of. So it's simply like this, F in the z direction squared. So if you want to find the magnitude, so that would be equal to the square root of, and then we have 1.92 times 10 to the minus 3 quantity squared, plus a minus 6.4 times 10 to the minus 3 quantity squared, plus a minus 12.0 times 10 to the minus 3 squared. And this whole thing will then be in terms of newtons. So let's try that. So it's this quantity squared plus 6.4 e to the 3 minus squared at plus 1.92 e to the 3 minus squared equals, take the square root of all that, and the force is going to be, it'll be 13.7 times 10 to the minus 3 newtons, and that would then be the magnitude of the force, like that. All right, so that gives you the magnitude of the force and the force in vector notation, giving you both the magnitude and the direction of each of the 3 components of the force. And yes, I did not put in the units, newtons over here, and Newton over there. All right, now we're correct. And that's how you do a problem like that.